Thank you very much for the introduction, and thank you for coming, in Exeter. Now, mine sites are a bit like Hollywood movies. They are the good mining environments, the blockbusters, the Oscar winners. By good I mean that these mine sites demonstrate the advances in knowledge we have made. These sites demonstrate how successful we have become in rehabilitating mine sites and how much knowledge we have gained on environmental processes operating at these sites. Then there are the bad mining environments, the second-rate midday movies with their poor performances. These mine sites show the gaps in our knowledge. They demonstrate how unsuccessful our rehabilitation efforts have been and how little knowledge we have of environmental processes. And then there are the ugly mining environments, the R-rated shockers. Nobody wants to see, at least not in public. These mining environments demonstrate the real challenges. They demonstrate to us what extraordinary rehabilitation tasks, remediation tasks wait for us, and how little knowledge we have of environmental processes. In this talk, I will give you an overview, my view, of mining and its environmental impacts and environmental processes. I will show you our advances in knowledge, the gaps in understanding, and the challenges ahead. One of the major environmental challenges we face around the world is acid mine drainage. It is one of the key challenges. Now, the science of acid mine drainage is exceptionally complex, but like everything, it can be made very simple. The best way of illustrating acid mine drainage is in form of an engine. And this engine runs on the consumption of sulfide minerals. The engine is started when we switch on the oxidation of sulfide minerals, when we expose the sulfide minerals to oxygen. So let's turn on the engine. Now, as the engine is being turned on, unfortunately you can't hear the noise in the background, the fuel in the engine, the other sulfide minerals, will dissolve. The sulfides release iron 2+, the iron 2+ will be oxidized with valuable oxygen to iron 3+, the iron 3+ becomes the oxidizing agent, it attacks the sulfide minerals, the sulfides release iron 2+, and the reaction go on and on and on. Acid mine drainage is also a huge bacterial infection. Acidothiobacillus ferrioxidans is one of the key agents infecting our acid mine drainage engine, the bacteria accelerating our reactions. As long as the engine runs, out of our exhaust pipe here on the right-hand side, there will be an acid metal-rich brew coming out of our exhaust pipe. This is the acid mine drainage water. It contains reaction products like sulfuric acid or dissolved metals. This acid metal-rich brew is commonly known as acid mine drainage or acid rock drainage water. It has a lot in common with Coca-Cola. It's got the same pH, it's got the same color, and is definitely of global occurrence. Now, in the last 50 years or so, we've made some phenomenal advances on our knowledge of environmental processes and also on acid mine drainage. And there are some very good examples, real Oscar winners, which demonstrate to the world that we've made these phenomenal advances in knowledge. And there is no better place to look at these advances in knowledge than Rio Tinto in southern Spain. Here we had the largest sulfide metal accumulation on Earth. There were over 90 mines operating, extracting base metals, copper, lead, zinc, gold, and silver. Rio Tinto is also one of the largest mining landscapes on Earth, more than 50 square kilometers. A mining landscape punctured by open pits and underground workings. littered with slag heaps, waste rock dumps, and tailing stands, and covered with abandoned mining, smelting, and transportation equipment. There is no topsoil, only barren ground. There's hardly any vegetation. What more do you or we want? Well, there is more. There is massive acid mine drainage from the headwaters into the Rio Tinto, down into the estuary, into the Atlantic Ocean, and we can travel the plume of acidity for hundreds of kilometers into the Mediterranean Sea. Rio Tinto is the ultimate nightmare for some. But for me, as an environmental geochemist, it's the Holy Grail. It is Mecca, it is paradise. What is so good about this mining environment? Well, firstly, we know that mankind was not entirely responsible for its devastation. There was natural acid rock drainage prior to mining, and the natural discoloration of the Rio Tinto most likely attracted the Phoenicians 5,000 years ago. But what else is so good about this mining environment? This slide demonstrates our advances in knowledge. Rio Tinto is the birthplace for acid mine drainage research. And it all started with Diego Delgado. Now, Diego was a priest in the 16th century. And in 1556, he reported to the Spanish king on the status of the Tinto mines. And Diego made some fundamental scientific observations. He reported that the reason why the river is known as Rio Tinto, which is Spanish for river of red wine — there must be some awful red wines in that part of the world — because it springs from vitriol. Vitriol, the medieval term for sulfuric acid. Diego was the first one to recognize one of the reaction products of acid mine drainage, sulfuric acid. Today we know a lot more about this acid stream. The pH ranges from 1.5 to 3.8, and the water is enriched in sulfate metals and metalloids. Diego also reported on the water chemistry. He reported that if you place iron in the water, it dissolves in a few days. Diego was the first one to observe the issue of iron dissolution from acid mine drainage waters, a common feature known today from acid mine drainage sites. Today we know a lot more about the iron chemistry. Yes, the iron is dissolved, but also the iron occurs as suspended solids within the water. Diego continued to report that no sand or loose material can be found because all the stones are fixed and stuck together. Diego was the first one to make the observation on the formation of iron cements within stream systems. Today we know a lot more about the diversity of these iron minerals sitting within the stream bed. We know that there are minerals like ferrihydrite, goethite, schwertmanite, jarosite, lottermoserite occurring with the stream bed. And we know that their occurrence is controlled by redox conditions, pH, solution chemistry. Diego continued to report that no fish or other life existed in this river, neither do people nor animals drink it. Diego was the first one to make the observation on the toxicity of AMD waters. Today we know a lot more about the biology of the stream. We know that Diego was only partly correct. Yes, there are no visible life forms, but no, there are more than 1,300 different microorganisms flourishing as extremophiles within this acid stream. Acid mine waters are haven ecological niches for extremely acid waters. Finally, Diego took a live frog and it threw it in the river, and it died without being able to leave the water. This cruel Catholic priest was the first one to document a toxicology experiment on acid mine drainage waters. Today, Exeter researchers wouldn't get the ethical clearance to do this kind of work. Diego was ahead of his and our time. At the same time, only 500 kilometers in the same year, a German, Georg Bauer, compiled a massive book on mining. With a name like Georg Bauer, which translates to George the Farmer, you will not be able to market your book and sell a huge number of copies. So what George the Farmer did, he Latinized his name. He called himself Georgius Agricola. Now, with that name, he wrote an all-time bestseller. He wrote De Re Metallica, the first systematic book on mining, mineralogy, and metallurgy. Agricola is not only the father of mining, mineralogy, and metallurgy, he is the father of many children. He is the father of geobotany. He made the world's first observation on metallophytes, metal-loving plants, plants which only occur over and grow in metal-rich substrates. He observed that over concealed ore bodies, metal ore bodies, the soil will produce only small and pale-colored plants, where a vein extends that grows a certain herb or fungus that is absent from the adjacent space. Today we know that these particular plant species may be of use to us for the remediation of contaminated land. Or some of our academic colleagues may argue that these plant species could be used for phytomining. George the Farmer is also the father of environmental impact assessments. He reported that mining operations impacted on the livelihood of individuals, and it also impacted on the environment. He gave the world's first observation and made the first environmental impact assessment. That the fields are devastated by mining operations. The water poisons the stream and either destroys the fish or drives them away. So it is said, there's greater detriment from mining than the value of the metals which the mining produces. Environmental issues associated with mining were not recognized in the 20th century by activists like Greenpeace or George Bush. These issues were recognized by 16th century scholars, Diego Delgado and Georgius Agricola. Since Diego Delgado and Agricola, we have made phenomenal advances in knowledge. There has been an explosion in the knowledge on mining and the environment. When you Google mining the environment, you get more than 240 million hits. Sorry, you only get 17 million hits for the University of Exeter. There has been phenomenal advances in knowledge. We've made phenomenal advances in knowledge on mine closure. We made phenomenal advances in knowledge on the rehabilitation of mine sites. We've made phenomenal advances on the treatment and prevention of acid mine drainage. And we've made phenomenal advances on predicting, using environmental indicators, or predicting environmental consequences on mining. For example, there are freely available resources on the internet available to forecast the environmental consequences on mining using the GARD guide, the Global Acid Rock Drainage Guide. It is freely available to all of us. And there are uncountable reports, publications, papers, meetings, conferences on mining and the environment. And there are some excellent textbooks, particularly this one, describing the fundamentals of environmental processes at mine sites. But there are still gaps in our understanding. And these information gaps are so obvious when we go to mine sites that have been operating in the 19th or 20th century and have been rehabilitated in the last few years and in the last few decades. These sites demonstrate how little we know of the environmental processes at mine sites and how unsuccessful our rehabilitation efforts have been. So let's have a look at one of these mine sites. I didn't dare to use the UK mine site. I quite safely chose an Australian mine site. Here we are at the historic Mary Kathleen uranium mine, and Ellie might remember that we've been there only less than a year ago in Northern Australia. The mine was operating from 1956 to 1982, Originally it contained 9 million tonnes of about 0.13% uranium oxide. In 1985, it was rehabilitated at the cost of $19 million. In 1986, it got an award for rehabilitation excellence by the Institute of Engineers. Well, I've got some bad news for the engineers. Let's trespass on the site and let's have a look at the details and the rehabilitation status. Today, the pit largely exists largely in the same form as it had existed when mining stopped in 1983. There are still remnant sulfide ore lenses exposed. To no surprise, you will find high uranium, high light rare earth element concentrations within these ore lenses, combined with high copper, arsenic, and nickel values. The radiation levels are slightly elevated, as they most likely are in this room. A mean of about 5.65 millisievert per year. There is significant wall rock oxidation, as you can see from these range of colors. No surprise, the pit water quality has been impacted, pH of about 6. The water is distinctly enriched in calcium, magnesium, and sulfate, as well as copper, nickel, and uranium. The pit should not be used for recreational swimming, but that doesn't stop the locals to go for a dip and to get more than a suntan. There are a series of waste rock dumps stacked around the mine site, 24 million tonnes. They're partly soil covered. They're only partly covered also with vegetation, as you can see in the distance. The waste contain high uranium, high thorium, high light rare earth element concentrations, plus a kick and copper, arsenic, and nickel. They're slightly acid generating. The paste pH 3.8 to about 7. And some parts are have distinct radioactivity levels, radiation levels, maximum of 24.5 millisievert per year. There's significant leaching and erosion of waste particles into the surrounding landscape, and to no surprise, the soil and sediments surrounding these waste rock dumps are enriched in uranium, thorium, light rare earth elements, copper, and arsenic. Since rehabilitation has completed, there has been natural colonization of the mine site by various plant species. In particular, there has been specific weed invasion, particularly the apple of Sodom. These plant species now experience bioaccumulation of certain elements which are enriched in the substrate, like light rare earth elements, copper, and uranium. And as a result, various species are enriched in metals, radionuclides, and rare earth elements up to 10 or 100 times the local factor. Apple of Sodom is a major weed which invades the site. However, the site is also used for cattle grazing. Now, stems and leaves of the apple of Sodom contain steroidal heart poisons, and the calcium, magnesium, potassium, sulfur values are well above fodder guidelines. As a result, these plant parts are toxic to sheep and cattle. When we move across to another domain of the site, the tailings storage facility, it's the tailings of the ground-up rejects, which are stored on site. We've got 9 million tonnes of uranium mill tailings. Incidentally, it's a massive rare earth element resource, about 50,000 tonnes, worth at least $5 billion Australian dollars. Now, when we look at these tailings repository, the tailings repository has been capped at mine closure, and now you've got natural colonization of plant species growing on the tailings repository. Today, 30 years after mine closure, there's seepage at the base of the tailings dam. Well, let's go down to the seepage area and have a look at the seepage point. The tailings seepage water is slightly acid, pH 5. Water is calcium, magnesium, sulfate rich. There are anomalous concentrations of iron, manganese, nickel, rare earth elements, uranium, and zinc. And we do detect radionuclides like radium-226 and uranium-235. As you can see, we've got classic yellow buoy formation, these iron phases forming in our waters. We've got evaporation of our acid mine drainage waters, and as a result we form these mineral efflorescences, these white salts in the distance. And these iron phases have enormous concentrations in various elements like cerium, lanthanum, arsenic, uranium, and yttrium. Seepage waters flow into the local creek waters. The creek waters have a pH of about 8.3 due to buffering from the surrounding soils. However, the waters are still saline, they're calcium magnesium rich, they have extreme sulfate values, very high uranium concentrations, and to no surprise, the creek sediment contains abundant sulfates, light rare earth element, and uranium enrichment. So 30 years after rehabilitation, we have got dispersion from the tailings repository into the seepage area, into the local stream system, particularly of uranium and particularly of sulfate. So what? What's new? Tailings repositories leak. There are more than 3,500 tailings repositories on our planet, and more or less every waste repository leaks. No, not quite. This site is special. It is very special. It is special because it demonstrates how wrong predictions can be, how wrong scientists can be with their predictions. In the 1980s, a number of leading scientists used laboratory experiments to forecast the waste repository behavior. They forecasted that the radionuclides would be retained in the repository. Any seepage would be only calcium sulfate rich. The seepage rate would be 5 cubic meters per day, and the water chemistry would be no threat, would pose no threat to local livestock. Well, these predictions did not come true. Today we've got significant mobilization of nuclides. Not only move calcium sulfate out of the repository, we also move acidity, metals, and nuclides into seepage surface waters. The flow rate is much higher than predicted, and the stock water quality guidelines are exceeded. In 1986, the mine site was rehabilitated to a standard appropriate at that time. The bond was repaid on completion, and an award was received for rehabilitation excellence. Today, there is seepage from the tailings stand, there's erosion and leaching from the waste rock dumps, the local soil, sediments, and waters are contaminated with rare earth elements, uranium, and sulfate. There's toxic weed invasion, particularly by the apple of Sodom, and some of the elements are bioaccessible to plants, and the elements are transferred into the above ground biomass. So 30 years after mine closure, some may say time is up. It's time to call Todd. What happened? Why did the predictions turn out to be incorrect? The predictions were made by leading scientists in their field, and they used state-of-the-art laboratories and fantastic infrastructure at the Australian Nuclear Science and Technology Organisation. The predictions were inaccurate because the company did not complete the capping exercise. They literally ran out of capping material. That was the first reason. The second reason is that the scientists completed testing on non-representative samples. The samples on which the predictions were based are not representative of the waste material actually stored in the waste repository. And thirdly, the predictions were partly based on assumptions. They assumed that the tailings contained clay minerals based on particle size distributions, but they did not conduct an X-ray diffraction analysis to determine there were actually clay minerals present to help in the absorptive capacity of the tailings. Mine sites like Mary Kathleen highlight the gaps in our understanding, and there are several lessons from this particular mine site. The first lesson is we should not award rehabilitation efforts too quickly. Let's leave it to the next generation to award us for our rehabilitation efforts. Rehabilitated mine sites need time to equilibrate with the surrounding landscape. And secondly, we need to get our predictions right. Clearly, our knowledge and our practices still require major step changes. And there's an extraordinary challenges and tasks waiting for us. The third group of mine sites demonstrate these challenges waiting for us. These sites demonstrate how insignificant our knowledge still is and what extraordinary rehabilitation tasks still wait for us. Today, the rehabilitation of mine sites still remains, many rehabilitated mine sites remain significant financial liabilities, despite the fact that mining companies and government agencies pursue the rehabilitation of these mine sites actively. They remain financial liabilities because they are characterized by 6 common diseases. They suffer land instability like soil erosion or slope failure. Local soils are contaminated with metals, metalloids, or acidity. There's significant weed invasion like the apple of Sodom. They represent public safety hazard, or they suffer from or enjoy acid mine drainage. Such legacy sites require innovative mine site rehabilitation. In many cases, the rehabilitation of mine sites relies on the use of plant species. So for this, let's have a look at a local example, and Hilke would be very much familiar with that particular site. In the 1980s, and only up the road, only 5 miles from here, tailings in the Cannon Valley were left abandoned. These tailings contain up to 0.3% arsenic, 0.1% copper, and they're highly acid generating, pH about 3 to about 6. The UK Environmental Agency decided not to spend any taxpayer dollars or pounds, and they left the site abandoned, and they relied on natural rehabilitation to fix the site. Something else gets fixed here. Now, 30 years later, the local native species have colonized the site. And the species which have colonized the site are largely gorse and heather. And gorse and heather are metal-excluding plants. So as the plants grow on the substrate, they do not transfer the metals into their above-ground biomass. So nature, and not the Environment Agency, chose the right pioneering plants to rehabilitate the site. Nature is showing us how we should rehabilitate mine sites in the UK. We know a lot more these days about the behavior of plant species growing on metal-rich substrates. And we know that we can classify plant species according to their metal uptake. There are certain plant species which have attracted an extraordinary interest, the so-called hyperaccumulators. These plants literally munch on metals. They transfer metals into their above-ground biomass up to weight percent levels. We know that for particular plants that they're capable to transport elements like arsenic, zinc, copper, cobalt, and nickel into their tissue. So much so that some of my academic colleagues proposed to use them for phytomining. And the idea is that we plant these hyperaccumulators on waste or sub-economic ore. We come around with a lawnmower, we collect the clippings, we throw the clippings into a furnace, and voila, we have the green metal ore. But phytomining remains an unrealistic approach to mining operations. The use of hyperaccumulators will have only applications in the remediation of shallow contaminated metal land. There's no potential to use hyperaccumulators for the mining of sub-economic ores or waste. Rehabilitation of mine sites has to follow much more practical and innovative principles, like the one demonstrated in the Eden project, where a kaolinite pit was converted into the Eden project. But there are much more innovative mine site rehabilitation practices, and sometimes with extraordinary solutions. In Germany, an indoor skiing facility has been built on a coal waste dump. A coal mine processing plant has been converted into a public swimming pool. In Poland, one of the major cathedrals is in an underground salt mine. And only in Italy you would have a cheese store in an old copper mine. In fact, there are 101 things to do with a hole in the ground. There are innovative mine site rehabilitation practices where mine sites have been turned into health spas, vineyards, botanical gardens, theme parks, wine cellars, saunas, shopping centres, football stadiums, and my favourite, the Bavarian beer town. So my final message is that we must seek innovative rehabilitation options. We must seek novel solutions for the rehabilitation of mine sites. We must do this today and into the future because the global mining industry is facing horrendous challenges. And some of these global challenges are an increasing demand for mineral resources, higher energy costs, particularly for crushing and grinding, limited or competing water resources, a decreasing grades in the material mined, more complex ores for our mineral processing experts, greater and deeper operations, and together with these operational challenges, there are social and environmental challenges. There are higher social expectations. We talk about a social license to operate. There are more environmental laws, and there is more waste being produced, and with more waste, there are more environmental impacts. More waste, in fact, a lot of waste. The forecast is that in the next 100 years, the mining industry will generate 2,000 cubic kilometres of mine waste. That is a mountain chain, 100 kilometres long, 10 kilometres deep, and it's 2 kilometres tall from here to Exeter. To no surprise, this was recognised more than 25 years ago by the United States Environmental Protection Agency. Problems related to mining waste may be rated as second only to global warming and stratospheric ozone depletion. And to no surprise, the United Nations took up this issue in the Rio 20 agenda, and they state in their Agenda 21 that humanity stands at a defining moment in history. Countries having mining activities face deterioration of environmental quality. Unless we do something, unless we continue to work on improving our environmental prediction and our rehabilitation outcomes. My research team, based here at the University of Exeter, Ellie sitting there, and a few others sitting on the other side of the world, in the University of Tasmania, established new environmental indicators for the mining industry. These indicators are there to forecast waste, water, and dust properties, and the research is funded by a range of agencies and industry partners. One of our research themes is the prediction of acid mine drainage. The common approach to predictive AMD testing, acid mine drainage testing, is based on geochemistry. So you simply analyze your sample using geochemical techniques. And you thereby use test protocols like the one produced from Amara, and you use static testing and kinetic testing. Static testing, you get analyses, data in an instant. Kinetic testing, the kinetic testing may take months or years to complete. As a result of the testing procedure, you end up with a waste classification scheme. In all cases, you end up only with two types of waste: the non-acid forming waste, the NAF waste, and the PAF waste, the potentially acid forming waste. Obviously, such a classification is far too simple. It's blinded by chemical data and obsessed with chemical analysis. And it tends to forget that sulfide oxidation is not only a function of chemistry, but also of mineralogy, texture, surface area, mineral hardness, and other parameters. So our approach to predictive acid mine drainage testing involves the integration of a number of tools and measurements. So we analyze and determine geochemical, textural, geometallurgical, and mineralogical properties. For this new architecture of testing, we've designed a series of new tools and tests for the mining industry. For example, we've developed a new pH test the microwave-assisted thermal energy pH test, or MATE pH. This test predicts the long-term water quality coming off waste rock dumps or tailings repositories. Traditionally, we use these kinetic leach columns to forecast water quality. And these kinetic leach columns have to run for at least 6 months to a year to come up with some indication of what the pH might be like in future. They also come at a significant cost of $2,000 per sample. Now, our MATE pH test does the analysis within a week at a cost of only $40. We've also developed a new acid mine drainage risk protocol, the so-called computed acid rock drainage risk grade, or CARD grade. It's based on the mineralogical analysis of samples for their carbonate content and their sulfide content. And using mineral liberation analysis and processing imaging software, we've designed a risk grade which allows us to predict AMD risk based on texture and mineralogy, and allows us to predict acid mine drainage domains within drill core. Traditionally, there has been a step change in predictive testing, and this is also true for the prediction of acid mine drainage. In the 1960s, we used qualitative observations to make forecasts on the likely water quality coming off waste rock dumps and tailings repositories. And people used simple correlations between the lithology, the rock type, and the water quality to forecast the likely pH and water chemistry coming off our waste repositories. In the 1970s, there was a step change. We introduced geochemical testing, static and kinetic tests. Much of the industry still uses these geochemical tests today, despite the fact that these tests were developed in the 1970s. In our research group, we've come up with a series of new tests which are being taken up by industry today, like the MATE pH or the CAR test or the GMT, the geochemistry, mineralogy, texture approach. These new tests and new methodologies represent a step change in forecasting environmental impacts at mine sites. Understanding mining and the environment is important. It's important to me, it's important to regulators, it's important to industry, and it is vital to humanity. In this talk, I've shown you a number of mine sites and associated environmental issues. We've come a long way from Diego Delgado to freely available web materials on the internet like the Guard Guide. There are some excellent examples, our Oscar winners, which demonstrate our advances in knowledge. However, there are still gaps in our understanding, like the Mary Kathleen mine site, which demonstrates that we have to get our predictions right. And there's still significant challenges ahead, and particularly we need to improve our rehabilitation. Thank you for coming.
Thank you very much. I'm sure that you have lots of questions, but I would like to ask you to just keep those questions to reserve. While I would like to make use of the opportunity first to offer a vote of thanks to Bernd for an excellent and entertaining lecture this afternoon. The thoughtful analysis of your critical mind highlights Bernd's developing the framework of mining, helping to promote acceptance of traditional mining in an environmentally conscious modern society. To this end, Bernd has shown that a broad overview of mine rehabilitation, as well as in-depth knowledge of aspects which are pertinent to the problem. The experience which he had in Australia occurred in many sites over the world, and therefore Bernd is on a mission to bridge the gap between mining and the academia, not an easy task. While searching for pertinent solutions, he has traveled all over the world until today with almost kind of treasure for given special attention. And I would like to not just he has been scaled the mountains of Himalaya, he has been in the jungle of Papua New Guinea, in the desert of Mongolia, and basically then he came to Cornwall.
The Holy Grail.
Bernd's first visit to Cornwall was in 2010, when he was here for a 3-month research sabbatical, and as a Lottermoser scholar had the opportunity to see the vast outdoor laboratory that exists in Cornwall with its high concentration naturally occurring of heavy metals and even higher concentration of heavy metals in sites where previously mining operations have taken place. Add to this a specialized flora which is developed on the mine site in Cornwall, and it must have seemed like a good place for an environmental geochemist to be in. By 2012, Bernd had joined the University of Exeter, and I must say, ever since I've appreciated Bernd's eye for detail, as he's with us today. Specifically, he has a keen eye for spotting environmental win-win situations. For example, when Bernd has a hunch that biosolids in municipal sewage sludge may contain significant amounts of gold, Bernd launched an investigation and found out that this was indeed the case. Bernd must have been crushed with pride when the findings of his research, ever the scientists, rather than going for gold themselves, were published in an article titled "The Noble Trap." It was clear that Bernd was on a mission to develop technology for integrated indicators which can address global problems economically and effectively. And I think what he has shown us today is that he is well prepared for the task that lies ahead. Hence I would like to invite you to join me in thanking Bernd in the customary way for his excellent presentation tonight. The floor is open for questions.
Long, hard day.
You think that the testing ever really will do this? Wouldn't a better approach maybe in the future to look at ways in different environments, different climatic conditions, different types of ore, and then to build a database of all those features to then predict what the new mine site might do?
Despite the fact that I've got this massive project on tests, I don't believe in tests anymore. The reason for that is that the mining industries need answers yesterday, you know that. So as they dig out material, they've got to know the properties of the material straight away. So I believe in sensors. Sensors which actually stick at the front end of your front end loaders, or which you can run over a rock face, and the sensors will tell you the rock properties. And these rock properties may be used to forecast waste or tailings properties. So tests, I don't believe in them any longer. There needs another step change, and the next step change has to be sensors, like prompt gamma neutron activation analyses, any of those. And there are some people working on it.
Do you think that could predict, or be used to predict, what the microbial community might be up to?
Oh, the microbial community, you really have to ask Chris. He's the expert in the audience. So I can't really comment on that. Yeah. Yeah. But for the industry, I see sensors are certainly the way to go, because sensors are used today now in the cement industry, in the phosphate industry, in coal mining. The sensors are installed, and it's time to actually for the mining industry, or the metal mining industry, which is very conservative, to lift its game and to install these sensors, which are commonly used in other parts of the world.
Do you think that the technology required to interpret the sensor data is of a mature variety, or is there still considerable work required to get a sensible interpretation from the enormous amount of data which can now be generated?
Yeah, of course, if you generate a lot of data, you have to have the computational aspects attached to it. You need some experts to interpret the information. But the sensors, their challenge is to produce reliable, accurate and precise information. So that the sulfur values that sensor analyzes for that shovel, with that dirt sitting in that shovel, is actually the true sulfur value as you would determine if you theoretically crush everything up and analyze it chemically for its sulfur content. So the sensor has to be able to do that. That's where the challenge is.
I just wanted to ask about gold in how do you think that it might be there in the first place? And secondly, is there ever going to be any commercial value in mining in the future?
Where does it come from? It comes from, of course, largely from your food intake. If you eat particular certain nuts, nuts have got very high gold concentrations. Other food products, of course, have much lower gold concentrations. So food products is a significant source. The other source are, of course, electronics industry, dental industry, dentists. The highest gold concentration is in the city of Pforzheim, which is the centre of the German jewelry producing industry. Contains 50 to 60 gram per ton gold in the dry mass of the sewage. 50 to 60 gram per ton doesn't mean anything to you. This is about 10 times the grade of a typical gold ore. So these are horrendous gold concentrations. On average around the world, sewage sludges, including the UK, about 1 gram per ton. This is sort of marginal gold ore. Can you get it out? Yes, you can get it out. The problem is if you would use, let's say, mineral processing techniques like cyanide leaching, you won't be very popular introducing cyanide leaching at a wastewater treatment plant. To sort of put it. It needs a step change in the processing technology. So on that technology or that reagent has to be environmentally friendly. There are other reagents available like thiourea and nitric acid and so forth, but they are still highly aggressive and they are of environmental significance. So there are no true alternatives at the moment. There's good research required. And Hilke and I have been talking about doing something on that.
Could I suggest you just, I've heard a rumour that the Toronto sewage place has actually put in smelters around it, is that correct?
It was done in the 1980s for a year or so. It collapsed again, it didn't happen. I actually put an exploration license over the sewage treatment complex of Melbourne some years ago. But the problem is, again, to get the gold or to get the metals out in a very efficient manner, and leaving a residue which is still usable for another purpose. Very, very challenging. But I didn't talk about that. Talk about something else. Might be another story, yeah.
Not related to salt scale. Do you think one day we'll be mining on the moon?
Yeah, people came up, there's a colleague of mine at the University of Arizona, he thinks we're just going to go out there and grab an asteroid because these asteroids are full of platinum, palladium and osmium and iridium and so forth. Just grab that one and bring it down to Earth. I think it's totally unrealistic, certainly in my lifetime, so also in yours, I bet. I think what more likely will happen is that we will mine the oceans, because ocean water is full of all the elements, including gold, and we can easily extract. It's technically feasible to extract any element out of the ocean. Whether we can do it at the moment in an environmentally friendly manner is a different story. And there's still vast amounts of resources left on our planet. There's this rumor going around that we're running out of resources, but it's actually not the case. When you look at element abundances around the world, there are vast amounts of resources left. The issue will be how we assign the land use of a particular part of our planet. Do we decide as a society we're going to mine this square kilometre, or shall we leave it alone? Well, the mining of ocean water, for example, happens in Cornwall. You can buy salt produced from ocean water somewhere on the Lizard Peninsula. So they extract the seawater, evaporate the seawater, and take the salt out. So it happens today. But we also can obtain uranium out of ocean water. And the Japanese research organization is looking at that. So all the elements occur.
Yeah, but what I mean is focus research and you kind of integrating different approach in one approach. So the mining technology and the research technology, but I want a different approach.
It will always be driven by economics. So if the price for something will reach a certain stage where the water treatment, the extraction of a particular element out of ocean water becomes feasible and economically viable, then it will happen. So economics will drive it, nothing else. Oh yeah.
On that note, we have time for one last question. Yes, behind.
Each site is its own problem child. So you really have to look at the sites individually, and then for rehabilitation purposes, the sites have to be divided up in domains because different parts of the mine site have got individual issues and requires individual rehabilitation tasks. So you can't take sort of learnings from or practices from one site, real practices from one site to the next site. That won't work. As long as you use the same technique, you can use the predictive tools, yes. But the rehabilitation is different to predicting environmental consequences.
Well, that's an interesting thought to conclude this session on. I would like to, first of all, thank Professor Lottermoser